work since 20 years. So since 20 years about digital twin concepts and its implementation for manufacturing and for smart manufacturing. So do you hear me or you want me to speak louder?
It's perfect.
Perfect, very good. So the presentation today will be centered in four parts. The first one, I will explain the concept of and functionality of a digital twin, the standards in the industry today. Then the second part will deal with the theoretical use case of flexible manufacturing system and how we implement we transform the simulation model, the traditional simulation model, the classic simulation model into a digital twin. So the second part will be on the theoretical use case. The third part will address a real use case, which is in our laboratory, Industry 4.0 laboratory at INIT. And I will depict with you, I'll show you how we've developed a digital twin, which is based on intelligent digital twin based on reinforcement learning using the deep Q network. And finally, I will close this presentation with explaining the hierarchical view of the metaverse and the digital twin. What's the immersive experience in the Industry 4.0 laboratory, how it can impact also all the learner experience. So let's begin by explaining the first part, which is the digital twin concepts and the related functionality and standards. The emergence of sensor IoT and IoT has led the development today of a cyber-physical system which integrate physical and computational components to improve the efficiency. That's the objective. So a key concept in the development of such CPS is the DT, which is, according to the definition given by Professor Negri in 2021, which is the virtual replica of a physical system that can be used to simulate, monitor, and control its performance. So DT evolved in response to modification in the associated observable manufacturing component, and dependently on the addressed application, the changes may include the updating the state, updating the geometries on manufacturing resources. So it depends on which type of digital twin we are addressing. The concept of DT depends on the nature of the application, which is why various types today exist of digital twin. In robotics, for example, the DT entails representing the individual components by their mechanical, electrical, kinematics characteristic for monitoring and health management. However, for production, planning, and control in manufacturing context, the DT is viewed as a virtual representation of a facility workflow. In other terms, we are not addressing the kinematics of the asset or the product. We are more interested about the facility workflow in the system. So a DT of this type is generally based on a discrete event virtual replica, that model the system evolution over time using a representation, so an abstraction which corresponds to the abstraction, the same abstraction used in discrete event simulation model, traditional discrete event simulation model that we worked with since 40 years now. So discrete event simulation models are among the most widely used operation research techniques for solving production planning problem. So how to use this abstraction and to construct a digital twin based on this discrete event simulation model. The Industry 4.0 have focused on cyber physical systems. So you can see here this graph. This framework. Here we have the cyberspace, and here we have the physical space. And in the cyberspace, what we found is all the modeling, simulation, decision-making analysis, all these steps are existent in our cyberspace. cyberspace. So the Industry 4.0 have focused on the cyber physical system and the Internet of Things to establish connectivity and integration of physical system. Now, the objective of Industry X.0 is to build on the connectivity established in Industry 4.0 to reach the intelligent digital twin based on those discrete event simulation model to enable efficient real-time monitoring and control of complex manufacturing systems. So here we are no more on just planning, production planning, but we are on the objective of real-time monitoring and control. I will show you later the concrete example of how we monitor and how we control those complex manufacturing systems. So some useful standards today for such digital twin implementation include guidelines for consistently performing credible GT modeling and specification that define the information model and data format. The most used, the most known, and is the International Organization for Standardization, ISO 23247, which is named the Digital Twin Manufacturing Framework and is intended to provide a generic manufacturing digital twin development framework that can be instantiated for case-specific digital twin implementation. Some other standards, which mainly are for other types of digital twins, such as the American Society of Mechanical Engineers and the International Electrotechnical Commission. So all of those give some standards around the digital twin. But the standard that encapsulate all the manufacturing system and is the one proposed by the ISO standard. For smart manufacturing, so the first work was proposed by ISO, entitled Automation System and Integration Digital Twin Framework for Manufacturing in 2020. This ISO series established a framework to support the creation of DT based on the notion of observable manufacturing element. And just, yes. So it contains 4 parts. The first part, this ISO proposed, is the overview and general principle, which contain the requirement for developing digital twin in manufacturing. The second one is the reference architecture, the part 2 of the ISO standard. Part 3 and part 4. Part 3 will discuss the digital representation of manufacturing element, list of basic information attribute for the observable manufacturing elements. And the final part is the information exchange. And it depicts the technical requirement for information exchange between entity within the reference architecture. All in this presentation, I will go through those parts of the ISO standard and how we apply them in the development of our digital twins. The first part, as I said, is the overview and general principle. The ISO, according to this definition, so a digital twin and the physical world depicted as observable manufacturing elements are connected and synchronized through data collection and device control. So as you can see here, this is the high-level concept of digital twin framework proposed by the ISO series. So as you can see here, a digital twin is an application. A digital twin is not a standalone model. So that's the principal things to be aware of, that all this is the digital twin framework for manufacturing. So the synchronization issue is very, very important. It's between the digital entities and the observable manufacturing elements. It ensures that the manufacturing system are constantly optimized as the digital twin receive the real-time system state from the physical system and send back the control decision. So that is the main characteristic of these digital twins. It has to be able to be synchronized in order to receive the real-time state and send the control action to the manufacturing system. So those are the definition in the ISO standard of what the digital twin must be able to do. So in terms of data flow, we can see here, this is an example showing what's the difference actually. Because we noticed that there is a lot of, now sometimes we have a digital model and we say we have a digital twin, and we don't know, we don't understand really what's the difference. So fundamentally, the difference in how the data flow is between the physical object and the digital object. In the digital model, which is the classic simulation, what-if analysis simulation model, the data flow is manual data flow. So we enter the input data modeling, we gather the KPI, and we continue this process, continue to ameliorate the system performance, the planning of the system. However, in the digital twin, the flow between the data flow between the physical object and the digital one is completely automated. There is no manual data flow between those two objects, which characterize the real digital twin concept. So we can see here, yeah, I like this classification because it's clear what's the difference between a traditional simulation model and the digital twin. Fundamentally, we can see here from this classification, offline, the simulation model is offline, as I said, for the data flow. However, a digital twin must be synchronized, it must be connected to the physical system. And connected to do what? To insert action, to execute action, depending on the nature of the steps. And also the difference, the main difference, very interesting to see is that the simulation model, traditional simulation model, are standalone. However, for a standalone simulation model, however, for a digital twin, we are talking about an application. We are no more talking about a model. Like we used to, for example, for simulation, a simulation model with Arena or simulation model with any other language. It's a model, a standalone, but now we are talking about an application. Let's see an application of this DT on a flexible manufacturing system, and I will depict how it works. So this is an example of a flexible manufacturing system consisting of 5 workstations. You can see the 5 workstations. And we have the intra-logistics haulage network. And we have the arrival of pieces is at this entry station. And we have the stock after producing the pieces. They are transported to the stock dependently of the nature of the type of product. We have 3 types of product, P1, P2, and P3. The intralogistics performed with a fleet of automated guided vehicles, AGVs, following a unidirectional path. So parts arrive at the system entrance and are stored in a main stock here. The upstream stock at each workstation, you can see here we have an upstream stock, which allow for waiting until the station become available. And the downstream stock enable the AGV to wait this stock, the downstream stock at each workstation. So for robust estimate of this flexible manufacturing system, what we used to do is to develop a discrete event simulation model. Here for this example, I have used Arena. So the number of vehicles and their speed are controllable parameters that can vary respectively between 1 and 9 AGV with a speed of 1 to 40 zones per second. And there are 3 possible AGV dispatching rules. So this is a classical problematic on a flexible manufacturing system. The first rule is to select the closest free AGV. When a workstation requests an AGV, scheduler select all free vehicles and then choose the closest. Cyclical AGV as a second rule. And the third rule is choosing randomly between a variable AGV. So I will show you rapidly what it looks like for how it works rapidly to understand how this yes. So here those are AGV. So this is a classical flexible manufacturing simulation model of a flexible manufacturing system. Pieces are placed here. And then we launch the request for an AGV, and the AGV comes. And each we have a flow corresponding to each type of product. Dependently on the type of product, this AGV are requested to transport the pieces all over the flexible manufacturing system. So this is a simple simulation model as we know it since now 40 years. For this, so the problematic herein is classic problematic of conducting simulation-based optimization to find the optimal configuration, which is the number of EGV, the speed, and the adequate dispatching rule that leads to minimize the mix span while ensuring EGV load balancing. So this is the classic key performance indicator for this type of problem. We couple this simulation model with an optimization model to find with this process of simulation-based optimization classic to find the better configuration of parameter of decision variables. And this is the mix span, evolution of the mix span. Now, let's see how we can transform this classic simulation model into a digital twin to control this flexible manufacturing system, because now we do not controlling this flexible manufacturing system. All what we see, what we can do is we plan the number of EGV, the speed, the dispatching rule, so we do planning. Now we will see how we could control those flexible manufacturing systems by transforming them into a digital twin. The first step to transform those classic simulation model into a digital twin is to transform this what-if analysis simulation model into an RTS. An RTS is for a real-time simulation model. For that purpose, we have this article. We have just, I will depict each steps. But for more insight, this transformation, you can see our recently published article in Winter Simulation Conference towards standardizing the integration of digital twin in manufacturing system. Have been recently presented in this conference to explain all these steps. So the steps, the first one is to define the synchronization point. According to ISO for part 4, here, the update frequency must be aligned with the real-time data needs and is to ensure accurate representation of the physical system. The second step is to establish the clock synchronization to ensure that the RTS advances continuously with the physical system. So it's important to use the world clock time instead of relying on the classic simulation clock, which uses to jump between the events in the discrete event simulation, classic simulation modeling. So here we no more use this clock, and we have to use the world clock time to embed the synchronization. And also we have to establish the communication mechanism using the protocols such as TCP/IP, MQTT, REST API. So we have to also establish this communication mechanism in order to be able to exchange between devices over the network. Here, so in order to define the synchronization point for this example, of flexible manufacturing system, so what we decide is to synchronize the pickup and the drop-off location. What does that mean? That means that when the AGV arrives to this node, we synchronize with the real system. In other words, we do not synchronize all the movement over each seconds of the AGV in the pathway. Why we did that? Because for sure we have issue with the synchronization, number of synchronization point. We cannot have a huge number of synchronization point, otherwise we will have a huge problem with latency. So now we add in order to do that with Arena, for example, we add a new element which named tasks from Simon language in Arena, which allow to do this, define those synchronization point. So it's important to understand that at this place, we no more use the delay, the classic delay that we used to in discrete event predictive model. Herein, we do not know when the AGV will reach a place. So we have to synchronize, this is a synchronization point, and when the AGV will reach these nodes, it will inform the digital twin in real time. I will show you an example of how it works. Also, we have to establish the clock synchronization with the run in execution mode, for example, in Arena, and establish the communication mechanism for Arena. We use the TCP/IP protocol to communicate with the real system. And we code this in a DLL that we load in the simulation model. So all these DLLs, this mechanism, are the application of digital twin. We do not have a model which is a digital twin. It's very important to understand this issue. So let me show you. So this is the real-time simulation that I just explained. So we load the DLL and we run in the execution mode for the communication mechanism. And also, I have developed for this, since this is, as I told you, this is a theoretical one use case. Next, I will show you a real use case. So in this theoretical use case, I developed an application, outside application, which is a manufacturing system emulator. So from this application, we will receive into the RTS, we will receive the information from the real system. Information of what? Of AGV responses. We will receive the AGV responses from this manufacturing system emulator, the arrival of work pieces. Also, I will show you, and you can see here we do the connection with the TCP/IP protocol. We have to define the IP address. We have to define the port to connect with the external application. And so now we go to the Arena model, and you see that we are initializing. We cannot we cannot launch the system. The communication will begin when I open the TCP/IP protocol. So now it works. So you can see in the window real-time configure control decision. Those are piece 2 at instant t equal to 0. At instant t equal to 0, need the AGV1 at station 1. So now I will send the response. The response from the real system is what does that mean? That means that the AGV reach this place, and it goes to P3 now. P3 at instant 30 seconds need the AGV2 at station 1. I will send from station 1 the response. You see, when I send the response from the emulator, the real-time simulator is updated. And that will allow to the system to be a virtual replica synchronized with the real system. So this is the RTS and how it works. And here we have a window of real-time system state monitoring. So this one, as I told you, a digital twin have to do two things. It must monitor and control. What does that mean, control? You can see here, P3 at instant T need AGV1 at station 3. Who decide that it must be AGV1 or AGV2? This is the intelligent module inside the digital twin. Okay, so this control decision are sent back. This control decision are found by the intelligent kernel and sent back to the real system. And that's how we can control, and that's how a digital twin, as I show you, a digital twin send back a control decision here to the system. And all this connection is automatically done. We do not manual insert data manually or decide manually, and the digital twin take actions. Those actions are those orders of the best AGV to send to each request. So this is how it works. This is a sample use case, how it works theoretically. Okay, so now let's move to, we have that, okay. So now let's move to define DT based on reinforcement learning. So I will dig more on explaining how this optimal decision, this intelligent decision of which AGV or which EMR I have to send in real time to the system, manufacturing system. So now this work will deal with a real case study, which is at the Industry 4.0 laboratory. And I will depict with you how we do the implementation with the deep network. So this is the real laboratory. What do we have in this? We have the phase 2 modular production system, which is here. You can see, composed of 3 fully automated workstations: the distribution workstation, the joining, and the sorting. Also, the role of this workstation is to produce the customer order received at the MES, manufacturing execution system, to mimic the make-to-order approach in the e-commerce context. The pickup and delivery are conducted by this EMR, autonomous mobile robot. This is also an EMR from phase 2 didactic. And it's allowed to pick up, so when a piece has been produced from this MPS, it is picked and dropped to, you can see here, this is the MPS. We have assembly station. So after picking up the pieces, the EMR will take it to the adequate assembly station to assemble the order of the customer order. So this is a learning factory that has been created to replicate a small-scale production system that is capable of fulfilling the customization and responsiveness requirement of Industry 4.0. The intralogistic operation, as I told you, involves picking up the produced work pieces from the MPS here and delivering them via the autonomous mobile robot to one of the manual assembly stations for assembly in the appropriate container. The items are then manually transported to packaging for delivery. This is the assembly station, manual assembly station. So this is the EMR bringing the work pieces delivered by the EMR, placed herein at the assembly station. And this is at the assembly station, the operator have to assemble the adequate package and put inside the customer order. So this is the operation conducted manually at the assembly station of the manufacturing system. So this work has been also recently, this work of developing a digital twin for this use case of intelligent autonomous mobile robot dispatching problem has been accepted recently in 2024 in the International Journal of Computer Integrated Manufacturing. This is the article of digital twin-based reinforcement learning to autonomous mobile robot dispatching. So in this work, what we have done This is the framework for the autonomous mobile robot dispatching problem. Our physical worlds, we have the cyber worlds, and in the cyber worlds, we have the DT layer and the mesh level. So when an order arrives, we launch the workpiece production on the MPS. After that, when the workpiece reaches the pickup location, sensors are read, the RTS is updated, and the sensor are read to update the RTS and communicate state. Communicate state for whom? For the intelligent layer, which is based on reinforcement learning. So we use the pre-trained, the offline trained model to find the best dispatching action, which means to which station, assembly station, it's better to bring the work pieces. So this is the framework of this intelligent DT. So to develop this DT, we have used, as I said, the ISO standards. So we design at the beginning, we design the DT observable manufacturing elements using the VML class diagram. So the digital twin services here of the class diagram. Class act as a mediator, ensuring that each physical action and state change in order or manual workstation, automated workstation, or the EMR is captured and reflected in the DT. And the observable manufacturing elements are the EMR, the workstation, we have the manual workstation, we have the MPS, which is fully automated workstation, and the work pieces, the orders. How the connectivity now and the information are exchanged. So in this DT application, two types of connectivity between the observable manufacturing elements was established. The first one is between the DT, the order, and the automated workstation, and it's based on the OPC-UA protocols embedded within the Turk RFID system. Actually, in this laboratory, the MPS, each station have an RFID reader writer, and each workpiece contain an RFID tag. So we can track at each entry and exit of workstation the workpieces. And in the digital twin, we take this data and we update in the digital twin model the state of the RTS. Also, the second connectivity is conducted between the DT and the EMR. So it's based on the REST TPA communication protocol, which is embedded in the EMR. So according to the ISO, these two protocols ensure reliable data exchange between those manufacturing devices and our DT. You can see rapidly, I don't know if I have time. Maybe this is the pieces when we are producing here the workpiece order, and then it's taken with the robot, the EMR, and transported to the adequate assembly station. And the order is done by this real-time simulator. So for efficient, now let's discuss how this decision, the intelligence of this decision, which mean to which the decision of to which assembly station to send the EMR in order to enhance the mix pan. So for efficient DT using control optimization, we use the control optimization rather than parametric optimization. Actually, the big advantages today of the RL models is that it allows that the training will be done offline. So now, when we are in real time, all what we need is to send the state and receive the best action to do. How it could be? It was done with the RL, which allowed to consider the online state of the environment and we benefit from the learning mechanism which can be done offline. So during the early learning mechanism, the agent interacts with the environment. So what is our environment here? Our environment here is the DES model. So as you can see here, our DES model is this is the simulator, and we train our real agent offline to define the agent receive the state that represent the environment and picks the action to be taken based on its policy. So for our application, for our DT, we have here five input layer, which is the number EQ. This is an example for two workstation, so two assembly workstation. So the decision is to which assembly workstation 1 or assembly workstation 2, given the real-time state of the system, to which assembly station send the EMR and we send our EMR. So the order arrives, we have our MPS after producing the pieces. The EMR is placed at this pickup point, and the environment is represented by this number in Q1, number in Q2, this is the number in Q1 before the assembly station 1, number of pieces, and the last pieces, because we have a setup time also, the nature of that last pieces in front of each queue, and we also have the next order to conduct. So this is UML sequence diagram of the offline trained model on the DS. And when we are online, we no more trained. Even though the training is consume times, but when we have the training done offline, there is no issue with the time. There is no more time issue, and we have our DT, which can. We have our actuator, sensor, and our RTS and our trained DRL. When pieces enter, we listen to sensor with the mechanism I explained in synchronization. When NGV comes, when the EMR need to be sent to an assembly station, we trigger the dispatching request. We send the dispatching request with the corresponding states to the optimizer. And we find the Q value as return to do the best action, which means which best assembly station to send for enhancing our system efficiency in real time. So since I will not have a lot of time, so I will, all those results are presented in the article. If you want them, can send me an email, I can give you the articles. Now I will go rapidly also through the hierarchical view of the metaverse and the DT. So the industrial metaverse is a 3D digital representation of the manufacturing system, integrating technology such as augmented reality, virtual reality to create the immersive experience. So immersion is a key aspect of the metaverse as it engages users interactively, creating a sense of physical presence within the virtual environment. This fusion enables interactive virtual environment that mirror real-world manufacturing system, enhancing collaboration and production efficiency. So today we are it's very common to speak with this industrial, we talk about this industrial metaverse. This is a framework, the hierarchical framework that have been also recently presented by Professor Elisa Negri, which I have published with her our other articles. So Professor Elisa Negri defined clarifying concepts of metaverse, digital twin, digital thread, and EAS for CPS-based production system. This is the article. So in this hierarchical, how the DT is at this place, and this is the metaverse. So this framework, which means that the metaverse can include one or more DTs and a series of other platforms, softwares, tools, access, and interfaces to grant the user experience and interaction that are not covered by the DT. The DT is considered a building blocks today of the metaverse, namely the patch which contains the model to represent the reality in virtual, from the synchronization to the real world to keep the model mirror the reality. But the metaverse is on the upside of the digital twin. So I've used the virtual reality to immerse students in our laboratory, and I give them the model which we have developed with simulation software to mimic the described factory. And to settle the high immersion mode, we use the render to Oculus feature, which is possible with Simu today, because Arena does not offer this functionality, but many new simulation software offer this possibility of using the Oculus to immerse in the simulation model. So students here use the virtual reality, the headset. They are asked them to develop this conceptual model of the learning factory. Also, I asked them to identify which synchronization points are most critical to tracking the DT to ensure alignment with the physical system while minimizing latency and data acquisition overhead. So I can show you rapidly here. This is my students at ENITS. So this is what they are seeing. They are immersed in the Industry 4.0 laboratory to distinguish, to be able to track this, to understand the conceptual model, to understand where to position their synchronization point also. To identify, also we had used this representation to identify the bottleneck of the system. So by applying this teaching approach, the following outcomes are observed. Immersion allows learner to effectively apply the conceptual modeling principle to design desks with different level of granularity. Learners gain proficiency in conducting input data modeling and the corresponding data collection step from the shop floor. And the learner successfully identified which sensor data to gather in order to synchronize the test model, enabling its integration in the DT framework. If you want more details about all this work on digital twin, say metaverse, my article, Teaching Simulation, Strengthening Digital Twin Development, also have recently been published in Winter Simulation Conference. I'll give more details on how we use this approach to teach on manufacturing system and the principle of DT development. So this is some reference, and if you need any other article, I'll be happy to share them with you. So, Professor Anjali, do you have?
I think we are good on time.
Yeah, very good.
So thank you very much, Professor Amel, for your very nice talk and making us informed about the recent developments in digital twins. Thank you. Now the floor is open for questions. If the audience has any question for the speaker, you can ask them now.
Hi, Professor. If it's possible, I have two questions.
Yes, please.
First of all, thank you for a valuable presentation. It was very good for me. Thank you. My first question is related to your presentation, slide page 12. At 12, you said that we have a digital twin, digital shadow, and digital object, yes?
Yes.
I think that it is not rational that we use a digital twin in all the problem and everywhere. Yes?
For sure.
Yeah, in which kind of problem we should use digital twin, and in which kind of problem we should use digital shadow or digital object? That was my first question. And my second question, what is your opinion that about using digital twin in autonomous vehicle, and do you have any kind of research in this area or not? Thank you so much.
Excuse me, for autonomous what?
Combination between autonomous vehicle and digital twin.
Autonomous what exactly?
Autonomous vehicle, the driver without the car without any
Okay.
driver. Yeah.
Okay, thank you.
Thank you so much.
Thank you. So very interesting. Effectively, we cannot use, it's very important that to understand that the digital twin, we need digital twin when we need real-time actions. So if we are not in the context of developing real-time decision, we are not in the need to develop this such real time. We don't need to develop this complex framework because, as you see, it's complex. And today it's still very complex to develop those because the connectivity and the exchange is not very easy embedded in the softwares. So we need digital twin. It's very important to understand that to when we need real-time monitoring, when we need this type of monitoring. And monitoring workflow all over the system, manufacturing system, is very, very complex. And today, I'm sure that there is no real application for monitoring in real time and controlling, because the problem of latency appears when the number of AGV or the number of EMR is growing very easily. So that's why it's very important to effectively see when we need those digital twin in the system. And the connectivity, you are asking about the connectivity of those digital twin to other robot. That was the question.
My question is related to any car without any car driverless car.
Exactly. It's for sure in digital twins, the objective today is to do the city digital twin. For that purpose, we need to have the GPS, but for those systems, we do not need discrete event simulator. We will need other type of simulator, like multi-agent simulator. But those simulator, if we want to use them to do actions, to send orders, to do actions, we have to link to connect them in real time with cars also. Yeah, and in my opinion, in my experience, the main problematic today is the latency. This system.
Thank you so much.
Thank you. Welcome.
Okay, so are there any other questions for the speaker? I will just ask one for the benefit of the people who are not from university. So for digital twin models, are there any specific hardware and software requirements for implementation, such as, many industries are using simulation for their decision-making processes. So if they are moving it to digital twin for different, let's say predictive maintenance or quality related decisions, do they have to have some special tools or softwares to make it work, or their existing infrastructure can be customized to make these decisions?
Exactly. For now, for the softwares and simulation, for example, some simulation software propose to do such inter-process communication, such protocols, how to embed the MQTT, but some others, maybe former one, are not so updated. So you have to do it by yourself. You have to code it by yourself, which could be also complicated. So I think that the advantages of using the new softwares is that they begin to insert those mechanisms in they offer those mechanisms, but still we have to develop the synchronization point to define all this stuff have to be done by ourselves. Yeah. So also for the metaverse, there is some open like Unity, but it's little bit complicated also to develop by ourselves all these virtual reality aspects in Unity, but we can use Simu or I think Flexim maybe also. They give the possibility to interact with the virtual reality paradigm.
Okay, thank you.
Okay.
So, if there are no other questions, then we would like to thank the speaker. It's a very informative talk. In the chat box, a few people have thanked you, Amel,
Thank you.
saying very nice and informative talk.
And if you have any question, I will be happy really to discuss with you. You can
Sure.
find the presentation and the article. I can send you the article. It's my pleasure.
Okay. Thanks very much, Amel, once again. And I close this presentation now, and we look forward to hearing Amel at another time in future. Thanks,
Exactly.
and have a great day.
Really,
Thank you, Professor Amel. Thank you.
thank you.